What's up, 7th grade? Mr. Pastel here. Last week we talked about rock layers and how you can tell if a rock is younger or older based on if it's above or below. So we learned that younger rocks, more recent rocks, are near the top, and the oldest rocks are near the bottom. So you have these stacked layers of rocks that tell you which rocks are older and younger relatively, relative to each other. So we call that relative age of rocks. We know that rock layers can get shifted around by plate tectonics, which we're going to talk about later. But today we're going to talk about how you can actually tell in a more precise way, how old the rock is. And we call that absolute age. So sometimes when a paleontologist digs up a fossil, if they use a certain technique, they can say, oh, this fossil is 43,000 years old or 3.7 million years old or 1.3 billion years old. And that's called absolute age of rock. The question is, how do we find that? Which is what we're going to talk about today. So how do we know the age of the Earth, the age of fossils, and the age of rocks? Remember that fossils are made of rocks, sedimentary rocks. Okay, so we can do this thing. It has a few names called radiometric dating, carbon dating, radioactive dating. So what is that? It's all based on something with radioactive decay. So what do I mean by radioactive decay? Well, as we studied earlier this year, the world is made up of a little more than 100 elements that are on the periodic table, but some elements are more unstable than others. What does unstable mean to you? Well, we know that the word unstable means yes, it exists in a certain way, but it might change. So for elements, that means that certain elements are more unstable than others. If they're unstable, they might change into a different element. And what can happen is, in the case of uranium, which we see, this is the reaction that nuclear bombs are based on and nuclear power is based on. So uranium is very unstable because it's so heavy. It has tons of protons and neutrons in its nucleus. So it's super unstable. It can change very quickly. So as soon as you destabilize it, it splits into two elements, barium and krypton. But it also releases a bunch of energy at the same time. And this energy is the basis of nuclear bombs. But if an element is unstable, it will decay into something else. So we call that radioactive decay. Radiation can also damage the human body. But that's for another day to talk about. So different elements have different lengths of time that they decay, different rates of decay. Let's zoom in on this. So actually, I'll introduce the term half-life. So half-life is the time it takes for half of a substance to change into another substance. So if I have, for example, a kilogram of uranium, after a certain amount of time, which we call half-life, I will have half a kilogram of uranium. Of course, I wouldn't want to hold uranium in my hands. So let's give some examples of half-life. I know this is getting somewhat complicated. So Carbon dating is one of the most common forms that we learn how old a rock is, or a fossil. So there's a certain version of carbon with an atomic weight of 14. Usually, most versions of carbon have an atomic weight of 12, but there's a more rare version of carbon called carbon 14. We call that rare version an isotope. So an isotope is basically a certain version of an element. We'll say an unusual version of an element. So if you start with carbon 14, it's a type of carbon. After 5,730 years, half of that carbon will turn into nitrogen. So you can measure rocks that are between 170,000 years old with this isotope of carbon. So actually you can kind of find out how old humans are, how long Homo sapiens, have been around using carbon 14. Let's look at potassium. After 1.3 billion years, that's quite a long time, half of potassium 40 will change into argon 40. And how do you actually measure these? You take a rock, you send it into a lab, and you actually can measure how much of an isotope is in that rock. Let's look at uranium. Uranium-238, which is an isotope, takes 4.5 billion years to decay into lead. So you can measure very, very long time spans with uranium. So if we were in school, I would have provided you M&Ms to do this lab activity. But actually what I want you to do is use coins, because I think you guys are more likely to have coins than M&Ms in your house. So what I want you to do is to get 20 coins. So I'm going to count out 20 of any kind of coin. I'm going to do that for myself now. 1, 2, 3, 4, 5, 6, 7, 8, 13, 16. So I have mostly quarters. So I have 20 coins. Those are going to be my model for carbon atoms. I know we don't fully understand this yet, but we'll get it in time. So imagine I'm going to gather them in my hands. Okay. So I have 20 coins in my hands. Every time I shake them around in my hands, that's going to represent 5,730 years, or one half-life. So what I'm going to do is shake them up, kind of like dice, and put them on a surface, and I'm going to see if they landed heads or tails. Okay? So let me point my computer down to them. Hopefully you guys can see that. I'm going to separate the heads and the tails right now. Okay. So I have... You might expect it to be 10 and 10, but because of probability and luck, it's not necessarily 10 and 10. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 12 heads and 8 tails. So, the ones that our tails, I will say, have decayed into nitrogen. So those are not going to change back to carbon. I'm going to write down those numbers on a piece of paper. So for my first, after one half-life, I still have 12 carbons, but 8 of them changed into nitrogen. And I'm going to write down those numbers. Now I'm going to set aside the nitrogens, because they're just going to stay nitrogens forever. And I'm going to take my 12 carbons and shake them again for another 5,000 years. Okay. I see a lot of tails, so I think a lot of them decayed. Oh, wow. Actually, I'm going to do that again. I don't think I shook them very well. I think in my hands they were a certain way. I'm going to redo that. Make sure you really shuffle them. Okay. A little better. Okay, so I have 1, 2, 3, 4. Oh, I only have four remaining carbons. The rest turn to nitrogens. Okay, so after 2 half-lives, I have 4 remaining carbons, and I believe it was, 8 that turned into nitrogen from my 12 that I started with in the second round. So, round 3. So after 2 half-lives, I only have 4 remaining carbons. So I'm going to shuffle them in my hand. Okay, put them on the table. I only lost 1 there. So after 3 half-lives, I still have 3 carbons. Let's do it again. I lost 1 more carbon into a nitrogen. What am I at? 4 half-lives now. 4 half-lives, only 2 remaining carbons. I lost 1. And I still have 1 more carbon atom, so I got to keep rolling this one until it turns into a nitrogen. So after 5 half-lives, I only have 1 carbon left. Let's just flip it. And I just lost it. So it took 6 half-lives to turn my 20 carbon atoms into all nitrogens. I'm going to give more details on how you guys can do this, but I hope we're starting to understand how atoms can decay and how long it can take for atoms in rocks to change. And remember, we use this to tell how old the rock is. So if I had 6 half-lives, let's just say 5,000 years times 6 half-lives, it took 30,000 years for all these carbons to disappear.